So while we're setting this up, let's start talking. So the talk that we discussed that we thought that you might like to explore this evening is about acceptance testing for continuous delivery. My background has been working in usually technically demanding organizations of what you might consider reasonably high consequence software. So software that's my background in the last 15 years before I started doing what I do now, which is consultancy, was working in low latency finance. So I was building systems that shows processing billions of pounds worth of other people's money sort of on a daily basis and all this kind of stuff. So I took testing quite seriously in those sorts of examples. One of my experiences was working for a company called LMAX, where we built, there we go. So we built LMAX, where we built one of the world's highest performance financial exchanges. So some of the lessons, so I think that LMAX is an interesting example because I think that we were absolutely world class at automated testing. I've not actually seen anywhere. Yep. So just go and I think we're okay. Good. That's all right. So this talk is really kind of framed by that experience. And one of the things that we learned was some tricks specifically around the practice of acceptance testing and some approaches that make acceptance testing a much easier to deal with problem. And so the idea of this is to explore those ideas. This is a slightly technical. It is kind of technical at the design level. I'm going to show you some code, but it's not very codey. But there's some bits of code ideas, and it's sort of design level tech is really what we're talking about. So starting point, where when we're thinking of things like acceptance testing, what are we really thinking about? This is my model for a deployment pipeline. I'm assuming since you're at this DevOps meetup, everybody knows what a deployment pipeline is. This is our mechanism through which we publish change to our production systems. All change to our production systems goes through the pipeline and is evaluated. The idea of the pipeline is that we're trying to falsify any changes through the course of the pipeline. And we divide the pipeline up into a series of stages in order to try and improve the efficiency with which we can get feedback. So the first stage, the commit stage, we're going to get very fast feedback. It's going to report back I generally recommend to my clients that they try and aim for under 5 minutes back from the commit stage. And then the next stage, so that those are going to be very fast tests. It's going to put a limit on the sorts of tests that we can run. And then the next stage is going to be acceptance tests. And acceptance tests are these much more complicated tests. In the commit stage, we're going to be writing the classic kind of TDD style tests. How many people practice continuous integration? How many people do test-driven development rather than unit testing? Okay, so let's spend 5 minutes me doing my eulogy on test-driven development because I think it's important. I think it's one of the most important techniques that we've learned over the last 25 years for improving the quality of code. There was an academic study that was carried out last year on production failures in production systems. And the most common line of code when a production system fails is should have implemented exception handling here. But apart from that, they reckon that 70% of the defects that happen in production would not exist if we only practice test-driven development. What test-driven development does is it does more than this, but one of the things that it does is it catches the kind of really common kinds of errors that we all make as programmers, the off by one errors or the inverting a conditional expression and all those sorts of things that we always do, whatever language we're using. Test-driven development eliminates those because they don't happen. And so if those don't happen, 70% of production defects, 70% of production outages don't occur. It goes deeper than that. So that's it from a testing point of view. I think it's much more important. So I think that test-driven development is really about a design practice and what's high quality in design. High quality in design, I would argue, is that there are 5 things that are crucially important, and I'm fairly certain that nobody in the room is going to disagree with my 5 things. You might add on some more things, but you're not going to disagree with my 5 because I think they've been true for as long as I've been doing software development, and that's a really long time. So the 5 things that are hallmarks of quality in software, to my mind, are it's modular, it's highly cohesive, stuff that's closely related is close together in the code. It's loosely coupled. There's a good separation of concerns. Stuff that's unrelated is far apart in the code base. What did I say? Modular, highly coupled, separation, and it exhibits information hiding. We have abstraction that draws lines in our code that means that we can alter one part of the code and the other part of the code doesn't care. I'm sure nobody disagrees with those. So what does it take to put those 5 things into code? I would argue that before test-driven development, the only thing that it took was the experience, the will, the determination of an individual programmer. That was it. It's just a choice. The only way that we got high quality in code was by somebody being smart enough and dedicated enough to bother to do it. Test-driven development is very specific. Test-driven development is different to unit testing. Test-driven development there's a little algorithm that you can operate for test-driven development. It's called red-green refactor. So we're going to write a test before we have any. It'd be the first thing that we do when we want to make any change to our production code is we're going to write a test to say what it is that we'd like the code to do. And then we're going to run that test and we're going to see it fail. So we're kind of testing that the test does what we think that it does. And when I do it, I tend to say out loud what I think that the error message will be. So I'm going to run the test. I say that I think it's going to fail with this error message. If it fails with a different error message, I've screwed up and I've not really written the test that I meant to. So I'll correct that. And then, so that's the red bit. I've run the test and I've seen it fail. Now I'm going to write the minimum amount of code that I can get away with writing, even if that's trivially simple, to make the test pass. And I'm going to run the test again, and I'm going to see it going to go green. That's the green part. And then I'm going to refactor the code and the test so that they're all elegant and beautiful and nicely factored, and they're in line with my design thinking as it stands at the moment. That's it. That's test-driven development, that little algorithm. So you have to be, so the most important thing is that you write the test first. And you'd have to be a quite obtuse kind of fairly strange kind of person to make your life more difficult and write the test in a way that meant that the code was hard to test. So it's naturally we're all a little bit lazy if we're any good. If we're any good as programmers, that's one of the facets of a good programmer is that we're a little bit lazy. We want the computer to do the hard work and us to do the thinking.
Can I understand the test-driven development as part of test the picture of the application, not the unit of my application architecture, for example?
Test-driven development is unit level. It's to do with a change in the code. It's focused on code level changes, not really application level features, which is kind of what we're getting to, because the focus of this talk of a screen that's out of focus is going to be acceptance testing, which is a little bit different. But I'm just trying to do this setup because I think it's important. I was reacting to the fact that very few people are doing test-driven development, and I think that this is more important actually than acceptance testing. So, okay. So we're talking about those tests that are close. These tests, when I write a conditional in my code, I want to know that it evaluates the right way. When I process something, I want to know that it returns the right value. If it interacts with another bit of code, I want to know that it calls that other bit of code. That's what the tests are for. It's to assert that the code does what I, as a programmer, expect the code to do. Okay? So you have to be an unusual kind of strange person to write that test in a way that's going to make your life harder and make the code is hard to test. So you're naturally going to try and write the code so it's easy to test. What you're really doing at this point, if you think about it, is that you're designing the public API to your code. You're designing, before you've written the code, you're thinking about how would it be nice to use this code. At whatever level that code is, you're thinking, what would make this easy to use and nice to use and pleasant to use? And guess what? What makes code at that level testable is it's modular. It's loosely coupled. It's highly cohesive. It exhibits information hiding, and it has a good separation of concerns. So now you've got this little three-step algorithm, red, green, refactor, that applies a pressure for the same stuff that we recognize as the hallmarks of high quality in code. It doesn't make a bad programmer great. It makes a crap programmer slightly less crap, and it makes a great programmer slightly more great. It's like an amplifier on the talent of a programmer. So if you want to do better job, if you want to write better code, if you want to have fewer defects and spend less time, being woken up at 3 a.m. because your software breaks, I would encourage you to explore test-driven development. If you've never tried it, try it. Go and look at some of the coding cartas, look at some of the online learning materials, get some help from somebody that's tried it before, any of those things, and practice it a bit. If you've tried it before and you didn't like it, go back and have another look, think about what it's really doing, because it's easy to get the wrong end of the stick, the wrong perspective. Writing the test first is really important. Writing the test afterwards is secondary. So that's a bit of a sidebar. We've kind of wandered off a little bit. But what's important about this stage is that one of the big advantages of test-driven development is because we're writing the test first, the tests that we write are loosely coupled with respect to the code that we're writing. So it means that they can be fast and efficient because they're unit tests, but also the code can change because we're designing the API to hide information from us, the implementation, because we haven't written the implementation yet. So if we're doing test-driven development properly, our tests are loosely coupled with respect to our code, so that our code can change and we can move very quickly. So this is all good stuff. The thing that test-driven development doesn't do is it doesn't really tell you that the system does what the users want it to do. That's an entirely different perspective, kind of the question that you were asking, I think. So test-driven development will give us this picture that the code does what I, as a developer, want the code to do. And what we'd really also like to, that's a really good thing to know. Does the code do what we think it should do? But does it also do what the users want it to do? Does it deploy? Does it run quickly enough? Does it fulfill a user's need? Is it configured correctly so all of the bits work together when I press the button to deploy it into production? All of those things would be really nice to know. And you don't really naturally, essentially get that from test-driven development. You might do, but you might not. And so that's what acceptance tests are for. So this is going to be the focus, really, for what we're talking about. And any evaluation that happens after the commit stage, the TDD, which is primarily the TDD stage of the deployment pipeline, are going to, you could consider as acceptance tests. But the ones that I really want to focus in are this stage. And this stage is specific. I have some reasonably precise definitions of what I mean by that. So acceptance tests are tests of the whole system that you're responsible from the perspective of an external user of the system, running in a production-like test environment, evaluating it in lifelike conditions, lifelike scenarios. If that sounds a lot like old-school functional testing, probably is, but I think that we found some better ways of doing it, which is what this talk is about. Everybody happy so far? So what is acceptance testing? So we want to assert that the code does what the users want the code to do. One of the really cool things about this is that we can start building this into our development process, and we can kind of start treating these things as executable specifications from the behaviour, and you treating them as kind of automated definitions of done and all this kind of stuff. I'm sorry to disrupt everybody.
We're sorry. Makes it more interactive.
That looks a lot better already. That's better. That's better. Thank you. Thank you very much. So yeah, well done. And thank you for the gentleman for giving up your seat. So the first thing is the focus. We're going to think about this. This really is from the user requirements. The test-driven development tests are more from the code angle. These are from the user angle. What that gives us, it gives us the opportunity to do it as a definition of done. If we start building in our team, the first thing that we do, so we also want to do test first, ideally. So when we get a new requirement to implement, we want to write the acceptance criteria for that requirement, and we're going to implement an automated acceptance test for every one of those acceptance criteria. An executable specification for the behavior of the system. And we're going to run that, and it's going to fail because we haven't written the code yet, so clearly it's not going to pass. And then we're going to develop, and we're going to do test-driven development to develop our code and build it up, and eventually we've got enough stuff, it's going to make that test pass. There's no more work to do. We're ready to go into production. That's how good the test should be. They should be telling us that there's nothing else to do after that point. So it gives us this automated definition of done. It asserts that the code works in a production-like environment. This is a real picture. So this guy is really firing a gun at, presumably he was the inventor of the bulletproof vest, because otherwise he's a very trusting, and I hope he's getting paid a lot. But we want to test that our code works in real scenarios. We want to test that, yes, that database is there when I push the button to deploy it, and yes, the messaging system is configured properly, and yes, the network works properly, and all of those things as well. So we want to test that we want our production-like, our test environments to be as production-like as we can make them, so they're representative of production, so that we, at the point at which we deploy into production, we know it's going to work because we've already rehearsed it in previous test environments. We want to test the configuration and the deployment of the system as well as the code itself and the behavior itself. So we want to test all of those things. One of the things that I put in the continuous delivery book is that I bet if you let me loose in your organization, I could break your production systems more quickly by changing its configuration than by changing its code. But on the whole, we as an industry tend not to test the changes to the configuration. We just hack away at it and go, yeah, that'll do. And occasionally it doesn't. We want to provide timely feedback. We want to know just in time that something is bad rather than just too late, as this man has found out. So we want to get information at a point that's early enough to be able to change what we're doing so that we can correct any mistakes quickly and efficiently. There's a lot of words in this space. There's a lot of terminology that I used in this space. I can give you nuanced descriptions of what's different about each of these things. I think for the purposes of what we're talking about this evening, you can consider all of these things to be synonyms. So acceptance testing, acceptance test-driven development, behavior-driven development, as it's commonly understood. Behavior-driven development is actually about both acceptance testing and test-driven development in terms of the ideas, but the tools that people tend to think about when you say BDD, like Cucumber and SpecFlow and those sorts of things, and I forgot what it's called, doesn't matter. The tools in that space are largely at the level of acceptance testing. It's largely where they work best. Specification by examples, a great book by a friend of mine, Gojko Adzik, that talks about some of these concepts from a slightly different angle, and executable specifications. I tend to use two terms quite a lot in this space, and they are acceptance testing, because that's the terminology that we used in the book to describe it, and so it's kind of part of the spot. I suppose it's kind of part of the pattern language, if such it is for that is continuous delivery. But I also like the concept of executable specifications, thinking of these things much less as tests and more about specifying desirable behavior in the system, because I think that puts your mind in the right context to be doing better work. So a good acceptance test is an executable specification for the behavior, so some behavior of the system that's desirable. So what's so hard? You know, that all sounds decent. Those sounds like good ideas, presumably. And if I'm honest, for as long as I've been writing software, which I worked it out recently, it was 38 years is where I'm up to so far as a professional software developer, which scares the hell out of me. But as long as I've been doing it, people have been trying to do this because it's an obvious thing to use computers to test the things that we build. That seems like an obvious thing to do. And on the whole, mostly for that period of time, we've been failing. Because this is hard. It's hard to do it right. And it's hard for a variety of reasons. The biggest one is that the tests break when the system under test changes. That nearly all organizations face this. They often establish a team of people to look after the tests, and they'll build some tests and they'll get them working, and then something changes, the tests will break and it's screwed from forevermore. So what that is saying, if we put our software developer hats on for a minute, what that's telling us is that the tests are too tightly coupled to the system under test. We know how to solve those sorts of problems. We increase the level of abstraction. We do use levels of indirection. Those sorts of techniques may give us a better picture. And then that's a lot of what I'm going to be exploring today. The tests are complex to develop. They're hard to set up. I had a client in the Netherlands a couple of years ago that were building an ERP system. They'd taken automated testing quite seriously, and they'd built this big ERP system with all these tests, and they had no clue what their test coverage was, because these tests were so horrible and complicated that if it was 2 weeks later, it took the person that wrote the test about 3/4 of an hour just to figure out what the test was doing, because the test was so horrible and complicated. So the tests are difficult to develop and hard to maintain, hard to understand. This is a problem of design. The tests are too tightly coupled to the system under test. They're not sufficiently abstract. They're not clear enough in their expressions. We can solve those sorts of problems. History is littered with the poor implementations of these. I particularly despise UI record and playback systems, because it's just, they're so fragile. You kind of I first used one of these in the early 1980s, and we kind of thought it was like magic. You could kind of record the user interface of interactions and replay it, and then you moved something, one character to one way or the other way, and all the tests broke. So it's rubbish. And I know they can be a little bit better than that, but they're not a lot better than that even today. Record and playback of production data. Just dumping production data isn't testing, it's just sampling. Really what you're doing when you just dump production data through your system is you're crossing your fingers and you're hoping that it's going to do something bad. But if it didn't do anything bad in your production system, it's probably not going to do anything bad in your test. It's usually the corner cases, it's the awkward things that catch you out in your systems in production usually, unless your system is complete rubbish. And so you want to test for those awkward cases. That's where you want to focus your testing effort. Dumps of production data into the test system and carrying them around, nasty automated testing products. So all of these things are kind of anti-patterns, and we shouldn't be doing any of those. We should eliminate those, and we should start thinking about other things. One of the kind of light bulb moments that I had, I was working on a big project, and we had a team, a separate testing and QA team that was looking after our functional tests. This is an absolutely classic. I would suggest that this is the most common practice for automated testing. This is what nearly everybody does if they do any automated testing. And I think it's a toxic anti-pattern. I've just said I've been doing this for a very long time, and if I'm honest, I've never ever once seen it work. So what happened with us, they had a relatively small suite of tests that they'd built a long time ago, and they spent all of their time, while there were nearly 200 developers building software, they spent all of their time trying to catch up just enough to make this tiny suite of automated tests pass. And they never did. The tests, while I was there, those tests never passed until we changed the game. And the way in which we changed the game was that we changed who owned responsibility for the tests. So if we do the stuff that we started talking about, if we start thinking about these things as executable specifications for the behavior of our system, what does it mean when a test fails? It means that our software no longer meets its specification. Who's responsible for that kind of problem? It's not a QA team, it's the development team. And what do you want when something breaks in that context? What do you want to do? What you want is that you want I use this as a general principle. You want the person that causes a problem to be in a position to witness the problems that they cause and be responsible for them so that they can correct the problems. And that way they learn more, they get to do better stuff, and the whole thing accelerates. So developers are the people that will break tests. So when a developer commits a change to software that causes a test to fail, it's the developer always on the hook to fix it. If you outsource that to some other team, you will never ever keep up. You want the developer in the loop. The other way of looking at this is at the point at which something bad happens like this, what do you want to do? You want to slow the developer down. You don't want them to go fast doing more damage. You want to slow them down, and you want them to fix things. So we want to make the developer's responsibility. And that was this was the light bulb moment that we had on this team sort of in the early 2000s. We thought, we should do that. And as immediately almost that we did that, we got the tests up and running, and they stayed running, and then we could start building more. Then we could start expanding the test suite and get better feedback on our systems. So developers own the responsibility for keeping them working. It doesn't really matter who creates the test in the first place. It could be members of the QA team, whatever. But as soon as that test starts running against code that's under work, it's the development team's responsibility to stay on top of failures. And that's pervasive. That's across all different test cases. Performance tests, acceptance tests, unit tests, integration tests, any of those, they need to be seen as part of the responsibility of the development team. I would argue that these are the properties of good acceptance tests. We want them to focus on what the system does, not how it does it. We want them to be isolated from other tests. So as we start to get more sophisticated, we can run them in parallel, for example. And that works well. We'd like them to be isolated from themselves in a way that we can run the same test over and over again against the same version of the system and get the repeatable results every time. That's a slippery idea than it sounds, but we'll talk about that in more detail. We want them to use the language of the problem domain because we want them to be easy to correct, and we want them to enhance our development process, not get in the way of it. We want to be able to test any change, whatever the nature of the change, we'd like to be able to evaluate that and test it, and we want the test to be efficient, because if we're going to get any good at this, we're going to end up with tens of thousands of these things in a system of any complexity, and we want answers in under an hour. That's hard work. So we need to take into consideration the efficiency of the testing that we're writing. We need to take the test more seriously in many ways. I'm going to go through each of these principles. The rest of my talk is really me going through each of these principles and exploring that in a bit more depth. I should have said at the outset, if anybody does have any questions, just interrupt me and we'll deal them as we go, because that gives the opportunity to explore in a bit more detail. If you're happy for us to maybe overrun the slot a little bit, then we can afford to do that. So if you want to do that, just interrupt me. But first, let's carry on. So what, not how. So here's a picture of a system. This is kind of a typical distributed system. It doesn't really matter very much what it is. I realized after I've drawn this, and I've been too lazy to get around and fix it, but the API that I chose is one that nobody outside the finance industry has ever heard of. It's called Fix. It doesn't matter. So this is a technical level API. If you've not come across that before, if you think of this as a REST API, it's not a REST API, but that's good enough. It's close enough for the purposes that we're going to discuss. So let's imagine that we've got a system like this. We've got a number of different channels of communication, largely representing different groups of users, different kind of bounded contexts of interaction with the system. And we've kind of got a public API, a trading API through the Fix system, trade reporting stuff. This is a trading system. And various other things that different users, different groups of users are going to interact with the system. So typically, if we want to write some automated tests for these, what we will do is we'll write test cases like this. And usually, the way that the vast majority of organizations do this is that they kind of combine, what the test does with how it's going to interact with the system. You've got to solve both of those problems. And so you tend to bung all of that stuff into each test script. What that means is if a change happens, let's say a change happens in the Fix API, it's going to break a whole bunch of tests. And now, the only way that I can get back into a working state is to go to each one of these tests, one by one, and correct the problems. That's a bit unpleasant. That's a bit of a maintenance overhead. But we know how to fix those sorts of problems in software development, in software design. So we can kind of raise the level of abstraction of our test cases, and we can add a level of indirection in between our test cases and the system under test. So we're going to have some code that represents those channels of communication with the system. So now, within our test infrastructure, we've got a thing that represents the Fix API. What it exposes, what the tests talk to it is abstract. So the test will say something like place an order, and this piece of code will say, I know what that means. It means that I've got to make this little message, and I've got to put these details in it to send it to down here. So now we've hidden the complexity of the communication in this level of abstraction. Now, if the Fix API changes, it invalidates our translation here. It breaks all of the same test cases, but now we only need to fix it here. and we fix it in this one place, and it fixes all of the test cases, because they're just saying place an order. They don't know anything about the fix API. The fix API is entirely hidden, abstracted away from them in this model. What you tend to do, as you start to explore this territory, what you tend to find is that there's a bunch of useful stuff that tends to crop up in this middle level, and some useful techniques. And this too is one of the things that we're going to explore in a fair amount of detail as we go through the rest of the talk. So it's about the nature of this test infrastructure and how that supports these fairly abstract executable specifications for the behavior of the system in the language of the problem domain. Oops. Okay, so the next property of our good acceptance tests is we want them to be isolated from other tests. We'd like to be able to run multiple tests and ideally against the same instance of the software and get predictable results. I think it's a reasonable statement. I can't think of any form of a testing which doesn't fulfill this first point. Any form of testing is about evaluating something in controlled circumstances. The key word here is controlled circumstances. We want to take control of the state of our system in order to be able to put it precisely into a state that we understand in order to be able to execute a test case against it. If we start thinking in those terms, then it's fairly obvious that isolation works on several different levels. So we want to isolate the system under test itself. We want to draw a boundary around what we think of as our software versus third-party software, which is our job to test. And we also want to be able to have these test cases so that they're isolated from one another, so we could run ideally two test cases in parallel with each other against the same version of the software and get consistent results. And then we want to isolate the test cases from themselves. This is temporal isolation. We want to run the same test over and over and over again and get the same results every time. So isolation is a fundamental part of the test strategy. A large part of the difficulty that I see in people that try and do these large-scale functional tests and struggle is that there's poor isolation, poor test isolation. So you need to treat it seriously. So we're going to explore each one of those in a bit more detail. So first, isolating the system under test. This is a really common pattern, particularly in big organizations. Let's imagine that we're all working on system B. We're building this system, and this is the kind of system that is downstream from system A and it's upstream from system C. And I don't know if most organizations, but a large number of organizations will say, you've got to test all of these together. You've got to test everything together. And there's a problem there, because if we're working on system B and we've got to, we're mandated that our testing strategy means we've got to deploy and evaluate all of these things together, that gives us some problems. So the first problem is it means that we don't really have control over the conversations to system B. So we can't do the interesting kinds of tests. So, for example, we can't test how system B responds when system A sends it rubbish, because we've got a real system A there, and unless we break it and make it send this rubbish, which is impossible because we don't have the code, we can't test that. We can't test what happens when the communications to system C is flaky. How does system B work then? What happens? We can't test those cases because we've got a real system C in the way. So that's a problem. And it gets worse than that, because if we're doing that, if this is a complicated system, our heads are full of our system. We're not really going to be able to fully understand this. We're probably not going to have best control of this. And so that too doesn't give us enough control. It's kind of like eating pancakes with chopsticks through a letterbox. You're trying to do something complicated at arm's length, and there's no way of getting there. You just can't get close enough. So that doesn't really work. It leaves system A in this indeterminate state. It means that our tests are not going to be very high quality. So this is an anti-pattern. This doesn't work. So what we need to do instead is that we need to isolate our system. We need to draw a boundary around our system. We say, that's our system, that's what we're testing. And we'd like it, whoops, sorry. Let me just step back. Sorry. Right, so what we'd prefer to do is we'd prefer to have our tests right up close to the edge of our system. They're still going to talk to our system through the natural boundaries. If our system, if system A talks to our system through a REST API, then when our tests come, they're going to talk through a REST API. If it talks through sockets, our tests are going to talk to our system through sockets. It's still going to talk through its natural boundaries, but we're going to do away with system A, and our tests are going to be right there next to it. That's what we really want. But there's a reason why organizations in this position want this end-to-end sort of testing. And the reason is that they're worried about the nature of these interactions. What happens if something changes in this interface between the two bits of the system and our bit stops working? And so there are techniques that we can use to worry about that as a separate problem. Yes? Maybe, but what I'm arguing is that I don't think it has much of a place, integration testing. What I'm saying is that there are other techniques that will give you more advantage, more capability in terms of the nature of the testing. No, not even at the later stage. The problem, fundamentally, if you think of any form of testing, it's about, you've got this black box of code. You want to inject some data into it. You want to collect some data out of it, and you want to examine the results. That's pretty much what any software testing is about. And so, if you've got other systems in the way, how are you collecting the results? How are you interpreting? How are you understanding what's going on? And this is particularly the case if we want to automate it. So if we want, getting close to the edge of the system is a more effective way. This is very specifically in the case when we don't own responsibility for those external systems. If they're part of our system, that's a different game. Okay? So I think that in an ideal world, what we'd like is something more like this. We'd like each of our systems to have these test cases that are close to the boundaries of the system and test that thing in isolation. The problem is, as I said before, is that there's a genuine worry. What if that changes? What we can do is that we could focus on, if we're in team B, we could write some tests that say, we expect this from system A. We expect that when we do this to system C, it does something useful. And when we do that, the number of test cases that we need to assert those interfaces is actually relatively simple and relatively constrained. We can go one step further, and if these are run by different teams, what we could do is that we could write those test cases, and we could give those test cases to the other teams. They could run them as part of their deployment pipeline, and if then they make a change which breaks our assumption of their system, they know that there's a problem, and they can come and talk to us or back out the change or whatever makes sense. But now they've got some information that they can do something useful with. That strategy is called user contract-based testing. And there are some nice tools in this space. So there's a thing called Pact that will do this kind of stuff at some levels. But this is a useful tool, a useful strategy. The next level of isolation that we're interested in is this idea of being able to try and run tests in parallel. And there's a caveat at the start. Most of my career for a very long time has been in multi-user systems of one sort or another. And I think most of us work in those sorts of systems these days. If you're working on a piece of software that only ever one person uses, this bit isn't relevant. But other than that, I think it's broadly relevant. So assuming multi-user systems, what we'd like to be able to do is that we'd like them to be so cheap to run that we can just almost feel that we can just create them, for every feature, for any behavior of the system, and and just keep getting really good feedback on our code. That's really what we'd like. So we'd like to be able to run lots of these things. But there's a cost to those things, and these sorts of tests in particular. If every test starts up its own version of the system, that's really quite expensive. That's a lot. That's a big overhead for every test. So it would be much more pleasant if we could start the system up once and then run a whole bunch of tests against one version of the system and get some results back. That would allow us to be more efficient. So really what we'd like to do is to deploy once and run lots of tests. So in order to do that, we need to find some way in which the tests don't interact with one another when they're running against the same system. And there's a really nice way of doing this. I have yet to find a problem domain where this doesn't work. I am suspicious that there might be some, but I haven't found any yet. But you use the natural functional isolation of the system. So for example, if we were testing Amazon, every test would begin by creating a new book and a new user account. And there, any changes would be isolated within that instance of the test run. The trading system that we worked on when we kind of came up with this idea was every test started by creating a new market in which we would trade, and new traders who would come into the market, and they'd put prices in. The test would put prices in the market, and then each test at the level of each individual instance of the test case running, nothing else is ever going to touch that market or that trader. So, testing eBay, you create a new account and a new auction. Testing GitHub, you create a new account and a new repository, whatever it is. And you can use natural isolation, the natural features, the behaviors of the system to isolate behaviors in a different system. At the end of the test run, your software will look kind of weird compared to production. You'll have loads and loads of books and accounts, maybe more than you would have, a different distribution of accounts and things in your test. But that doesn't really matter. It gives you this isolation. And it allows each test to be absolutely specific and prescriptive about the state that it wants the system to be in before it starts executing the test. The other part of this is temporal isolation. So the other aspect of this is that we'd like to be able to run the same test case over and over again and get the same results every time. So here's a little example. So here's a made-up test. We've got a store, and we're going to create a book in the store as part of the setup of the test. We're going to place an order for the book. It's a very good book. And we're going to assert that the order's been placed at the end. That's the test. That's a real executable test case. This is the first version of this kind of abstract level. Think about it for a moment. It says absolutely nothing about how the system works. All it says is the behaviors that we'd like of the system in the language of the problem domain. The problem with this is this is the interesting line for this case, and this is the problem line, because if we run this test twice, we've got a problem. So the first time we run it, somewhere deep in our system, there's going to be a data store of some kind. Doesn't matter what sort of data store it is. And when we run that line saying create a book, somewhere in our system, we're going to end up with a book. And then we run the test again, and the book already exists. So what do we do about that? Well, we can cheat. We've got this layer of infrastructure. So when our test case says create a book called continuous delivery, our test infrastructure, I'm anthropomorphizing now, but our test infrastructure is going to say, yeah, you don't really care what it's called though, do you? I tell you what, you carry on calling it continuous delivery in this instance of this test case. I'm going to call it whatever I like, and I'll map it for you. So every time you look at it and you use the word continuous delivery, I'm going to map it to what's really going on. So what we'll do, the first time we run it, we're going to create a book called Continuous Delivery 1, 2, 3, 4. The next time we run it, we're going to create a book called Continuous Delivery 6, 7, 8, 9. We're back to having functional isolation. We can run the same test over and over again, be absolutely specific about the test cases it wants. In its context, it's using this idea, it's mapping this to continuous delivery, but the first instance of the test case maps continuous delivery to 1, 2, 3, 4. The second one maps it to 6, 7, 8, 9. This is a really, really useful technique, and we ended up doing this for all of our functional isolation entities. So any kind of entity that we created in the context of a test, we would just name mangle it. So alias your functional isolation entities, give them a made-up name, and use your test infrastructure to map to and from it, and it gives you this way to go really fast, building the stuff that your tests need, and have each test absolutely isolated from itself and every other test. We want our tests to be repeatable. We want our systems to be deterministic and our tests to be repeatable. And if we've got the kind of system that we were talking about before, it's not really deterministic because we've got this other external system in the way. So here's our system, and if we kind of learnt to program from somewhere other than Visual Basic for Dummies, we're probably not going to write it, just talking direct to that. We're going to have a layer of code in here, and there's going to be, the communications channel that this talks for, the technology, the sockets layer or the REST API or whatever else it is that sits there. And the external system talks to our system like that. And we already said we don't really want the external system if we want our tests to be deterministic. So what we could do instead is that we could stub out the external system. So at the point at which we deploy in a test environment, we could say, so the configuration for this bit is exactly the same or pretty much the same as the configuration for this bit. The only difference is the way in which our test talks to it simulates the conversation that's going on from the external system. So we're going to effectively mock all of our third parties and fake them. And that allows us to inject data into our system to get it into the state that we want it to be in and to invoke the behaviors that we want. And it allows us to collect data out of our system so that we know what's happening, without breaking the encapsulation of our system at all. We're only talking to it through natural interfaces. If we start doing that and we start building infrastructure, it starts to go a bit further. So here's a bit more of a system that we're talking about as a public interface. This is the scope of the system under test. We're going to have some test infrastructure. And we're going to have some test cases, these scripts that describe the behaviors in the language of the problem domain. And our test infrastructure establish a back channel to these stubs. So our test cases, now we can start building a language around that. We can express ideas about, send this order from system A. It's going to talk to this thing, which is pretending to be system A, and it's going to fake up an order, and it's going to inject it into the system under test. I have this mental image of us kind of being like scientists trying to put probes onto our system, and that's really what we're trying to build here. We're trying to build a test rig, some test infrastructure where we can insert our system and measure it and figure out really what it's doing in quite sophisticated ways. All of this has kind of been leading up really to this. This is the kind of slam dunk for me, this idea of using the language of the problem domain. Have people read the Domain-Driven Design book by Eric Evans? One or two people. I would recommend it to you. So what domain-driven design really is kind of fleshing out some of the ideas of object orientation in some ways, which is really about building simulations of our problem domain in the software that we create. And one of the ideas in the domain-driven design book is the idea of using an analysis technique called establishing a ubiquitous language. You establish a language in which you can express ideas in the problem domain, and as your understanding of the problem grows, you enrich the language and you share it, and everybody uses it. So not just the development team, but the product owners and the business owners and everybody that's involved in the system learns the language, and you have in very formal settings, you might even keep that version of that language, a glossary or sort of terms and stuff. So, if somebody uses the word market instead of using the word, trading venue or something like that, then you'd say, oh no, you meant trading venue. You get pedantic about this. And one of the things that's really valuable is, so one of the advantages of this idea of a ubiquitous language is it means that we can have really rich conversations about the behaviors of our systems, and there's very little room for translation errors. So when the product owner says, I've got this great idea, we need blah-de-blah-de-blah, I'm going to say, oh yeah, I know what blah-de-blah-de-blah means, because we share the ubiquitous language, and I'm thinking in terms of code, and she's thinking in terms of the behavior that users want. And so we're kind of communicating much more effectively. And the language that we can start to use for our test cases is the same language. So this means that there are no kind of impedance mismatches. There are no kind of losses in translation throughout the development process. A simple domain-specific language. We can create a computable grammar, a computable language that allows us to express these ideas. It doesn't have to be deeply complicated. But we can do these. And if we do that, it means that it's really easy to create new test cases, because it's almost like writing English or Portuguese. It's almost just writing it in a natural human language. Just the grammars are slightly more formal just to make it computable. It means that we can read it. It means, so one of the tests of one of these domain-specific languages is that you imagine the least technical person that you can think of that understands the problem domain and be able to show them any of your test cases. They should be able to read them and understand what it means. One of my friends worked with a client that was an airline, and if you were using their online reservation system and you phoned up their support people to talk to them, the information that they had about the behavior of the system was the executable specifications for the behavior of the system. These were the test cases that had run against precisely the version of the software that was in production. So when the person's on the phone saying, well, the software works like this, they're absolutely bloody right, because that test passed. They're reading, that's a very strong assertion, a very strong understanding of what the software is really doing. It means that we can start building this infrastructure. It means that we can kind of abstract these layers. We can start building this abstraction and separating what it is that the system does from how it does it. The product owner doesn't care about how the system works. They care about what the system does, so we can express the ideas. It also means that you can build these things really fast. I put my hand up. I haven't measured this, but subjectively, what I've seen with my clients, I recommend this to clients, and this is one of the things that kind of resonates with clients quite strongly, because this is a silver bullet. This is a really, really valuable technique. And one of the ways for coaching organizations that are trying to adopt continuous delivery and have a heavy manual testing is automate the manual testing. Just automate whatever the organization does before they release the software, automate that. Because it's manual testing, it's going to be a small set compared to what you really want. And so that's a really good place to start. And that sounds really scary, except if you start using this technique, automating those test cases takes probably only a little bit longer. Let's say 10% longer, maybe 20% longer than just doing the manual test case for once. So if you run so immediately you've run released twice, you've won by doing the automation, because the next time you run, the automation will just execute and it will just and it will give you results in no time flat. So this is a really big step forward if we're able to do this. So the ability to write these test cases fast, quickly, and efficiently, and anybody can kind of understand them. The objective here is not intentionally to try and allow non-technical people to write the test cases, but it does kind of work. I've seen that happen because the language is so abstract. But that's not the objective. And lastly, it gives us the opportunity to abstract complex setups and have one line. So nearly all when we were building our financial exchange, nearly all of the test cases, the vast majority of them, began by creating a couple of users. First, you'd want to be able to have a market maker who could put prices into a market. You'd need a trader to trade against them, and you'd need a market. And in order to do all of that and do that without breaking any of the encapsulation of our system, doing that through all of the normal behaviors of the system, it was about 12 or 15 different interactions. We had to register new users. We had to go and get an authorization from a third party to say that they were valid to trade. We had to set up market, all of these things, and we could do that in one line of code, encoded in our. So we would just say, we want a market with these prices in, and it would do all of those things behind the scenes. So we could do it really quickly. In terms of writing the line of code, we could do it really quickly. So here's some examples. So this is real. These are real test cases where I took the code, and the style that we tended to use was not have a separate language, but just It's a thing called an internal DSL. So this is built on top of Java. So there's Java, and it looks a bit Java-y. So you've got things like dots and camel case. But if you imagined replacing the dots with spaces, and the camel case, you inserted spaces, this is completely readable by somebody who only understands the problem domain, who's never seen Java before in their life. So this is selecting a deal ticket. A deal ticket is a concept that's common for a particular instrument that we're going to trade in. We're going to place an order. We're going to check a feedback message. We're going to dismiss the feedback message, place another order, and check the feedback message again. Here's another one. This is through the fix API that I was talking about before. So imagine that's a REST API. So should successfully place an immediate or cancel by market order. If you were a trader, you'd understand the details of specifically what that meant. And so we're going to place a mass order, which is something that we can trade against. That's one of those instructions, those mega instructions we're talking about, doing lots of different work behind the scenes. And then we're going to place an order to trade against it. And we're expecting those to bump into each other and form a match in the exchange. Again, there's nothing here really that says much about how the exchange works or the technology underpinning it. The setup for these is kind of what I talked about before. Each test creates its own circumstances. It assumes that the system's already up and running, but apart from that, it's going to create a marketplace in which to trade. It's going to create a user, create a market maker user, and it's going to log in to be able to do the trade. The next layer down of the code, the implementation of the language, which is shared between all of these test cases, is interesting too. So this is the implementation for place order through the user interface. And you can see that there's lots of optional parameters. So again, in order to be able to go very quickly, to write test cases really quickly, if I don't care about the detail of the order, I can just say place an order, and it will make up stuff for me that will just work. If I want to be dead precise and be really specific about the details of the order, I can fill those details in too. And it will do all of this, and it will translate all of these things, and it will just work. This is the equivalent. Sorry, I haven't got the equivalent. So the equivalent for the fixed one was even longer with more optional parameters and so on. We did this for a while. These are, as I said, these are real test cases, and we kind of came to a realization. Actually, there was still a little bit too much information about how our system worked in here. So it was talking about trading user interfaces and fix APIs. And that's technical detail, really, that shouldn't be in the test. So we changed it, and our tests ended up looking like this. So this is one test case, and this test case can work against 3 different API technologies. So the first one is through the fix API that we talked about. That's the institutional trading stuff. The second one was through the user interface, the web-based user interface. And the third one was through a public API where you could write your own trading systems. If you're placing an order for things, and you're only thinking in terms of placing an order, it doesn't matter which one of those things, the scenario is going to be the same. So we're going to place an order. So this is an immediate or cancel by market order. That's the same kind of order that we were talking about before. We're going to place an order, and it says all of those things, that it sets those up. And then we're going to wait to see that order was matched by another order. That worked for all of those 3. We could run that. Our infrastructure could run this one test 3 times, once for going through the fix API, once through the public API, and one through the web API. That's interesting, I would suggest that's interesting, even if you don't have that problem. Because what that's saying is it's pointing out how loosely coupled these executable specifications are from the implementation of the system. If I can do this, that means I can rip out and throw away my system and rewrite it completely differently. If let's imagine that we come up with a thought-driven way of trading, I can just add that as a channel. This case is still valid. We had a case where we were about 3 weeks away from going live with the first version of our system, and we've been doing trading through a regular user interface that was just kind of, you filled in a form to describe a trade. And the product owner came up and said, oh, we've had some really good ideas. 3 weeks before we're going to live, instead of releasing with the boring old trading blotter, we're going to release with a game first up, just to see how things go. And we were going, huh? And they said, yeah, it's going to be really good. What we're going to do is that we're going to draw a graph on the screen for a marketplace, and you just guess on whether it's going to finish above or below the starting price after a fixed time period. And we're going, huh? We had tens of thousands of these test cases doing this, but they were all written like this. And actually, when we stopped and thought about it, placing an order is still placing an order. Whether it's a click on a graph or filling in a form, it's still placing an order. So we kept all of our tests. We implemented a new device driver thingy to click on the graph instead of filling in the form. And all the tests stayed working when we built the new user interface. This is really, really powerful. I had a client, I mentioned them before, built an ERP system. They wrote the ugly tests. I put this before them and they went, hold on a minute, we can do this. So they rewrote. They started rewriting their test. What they were doing was that they were essentially re-architecting their system. They got this reasonably successful product as a monolith for an ERP system, and they wanted to move into a more distributed microservice style architecture. And so they wrote the tests using this kind of technique against the old version of the system, demonstrated that those, and then they wrote these device drivers that would also work for the new version of the system. So that now they got a test suite that worked for covered both sets of the system, and as they were building the new system, they got the executable specifications for the new version of the system. And they knew that it was kind of behaviorally consistent between the two systems. This is really quite valuable stuff. We want to be able to test any change. So test cases should be deterministic, and one of the classically difficult things in trying to make test cases deterministic is time, because time is just moving on all of the time. And really, I think that there are only two strategies that you can employ when it comes to time. You can either ignore it. You can, if your system doesn't care about time very much, you can kind of blank it off and just not compare. When you're looking at results, you don't bother comparing the results with time in them. Or you take control of time as part of your testing strategy. So let's examine those in a bit more detail. So the first one, you ignore it, you just filter out time-based values in your tests. The advantage of this is really trivially simple. It's really easy to implement. The downside is that you can miss mistakes if your system does care about time, and it really prevents you from testing complex scenarios where time is a real factor in your system. The alternative is a little bit more complicated, but probably not quite as complicated as we might first think. The best way of doing it is treat time in the same way that we treat the external third parties. Treat them as though it's an external resource, and basically fake it in the scope of the tests. So this is really flexible. We can tell the system to understand whatever time we want it to understand. We can fast forward in time. And we can simulate any time-based scenario with time under our control. So one of the things, particularly in trading environments, is that you have fixed periods. So you have things called clearing periods, and it's classic. If you write probably nobody writes checks anymore, but when we used to write checks, you'd write a check and the actual check wouldn't get into the bank until for 3 days. That's because there's a thing called clearing going on. And the clearing processes are they're archaic, but they take 3 days to go through. So if you want to write a system, you could write a system and then wait for 3 days to see if it does it, or you could cheat and you could fast forward through time and evaluate that in a few milliseconds. The downside is it's slightly more complex infrastructure. So here's a test case. This is all of the other test cases that I've shown you so far are at one level or another real test cases that I've really executed. This is a slightly more made up one, but it would be executable. So we should be overdue after a month if we borrow a book from a library. So we've got a library. We're going to borrow a book called Continuous Delivery. Very good book. And we're going to assert that the book is not yet overdue. Then we're going to time travel forwards 1 week, and we're going to assert that the book's still not overdue. Then we're going to time travel forwards 4 weeks, and we're going to assert that the book is now overdue. So clearly the interesting things here in our domain-specific language are time travel. That sounds like a hard thing to invent, but we're software developers, so we've got control of the universe. So here's our test infrastructure, and if you're writing any system like this that cares about time, somewhere in your code, whatever your language, you're going to have a line of code that looks vaguely like this. You're going to be calling out to the system to ask it what the time is. And the only way that we can kind of manipulate that, if we do that, is to change the system clock on the computer, and you get into all sorts of messy, complicated stuff if you start doing that kind of thing. So we probably don't want to do that. So we could cheat. We can put a level of indirection between our code and time. So instead of asking the system the time, we're going to ask a piece of our own code the time. So we'll have our own piece of code called a clock maybe or something, and we're going to always ask it the time. And then we could implement our own version of the clock, and by default, all the clock does is it just returns the system time. It just says, yeah, it just does what it did before. We just added a level of indirection. But when we're running it in a test environment, we can cheat. So we can have our test infrastructure. We have a test case that says time travel forwards 1 week, and our test infrastructure says, okay, so a week is blah-de-blah-de-blah milliseconds, so I'm going to tell it to time travel forward in milliseconds rather than weeks, because that's for humans to read rather than machines. And I'm going to communicate that to this back channel, and the back channel is going to tell our clock to lie to the rest of the system, and that the next time it asks, it's going to tell it what time to say. So we have the clock under precise control. That way, we can execute these long-running scenarios, or we could evaluate. When we were releasing our exchange, we had about somewhere between 20 and 30. It was about, I can't remember, variously during different parts of the history, somewhere between 20 and 30 different external third parties. And nearly every time that there was a daylight savings change, one or other, or often multiple of those third parties would fail. And our system never did, because we wrote code that tested. We would fast forward to the next daylight savings change and then watch the code behavior over the daylight savings change and see if it still worked. We'd thought of that one. You're never going to think of all of the conditions for the test, but we'd thought of that one, and so we tested for it, and that never happened to us. This gets into more tricky territory. Remember, we said before, what we'd like to be able to is deploy our system and then run a whole bunch of tests in parallel against our system. If we're time traveling, we can't really do that. And so we will probably want to treat these tests specially. We probably want to deploy those and give them a dedicated version of the system, because you can't time travel in 2 different rates. The system would mess up big time. So what we did is we tagged each test with, interestingly different tests with an annotation. So here's a test that needs to fake time, so we tag it as a time travel test. Here's a test that's destructive. We're going to destroy bits of the system while it's running to see how it copes under stress. Here's a test that needs a particular piece of hardware to run against, and so we want to deploy that to a test environment that's got that hardware in it. And then we could imagine that we have a piece of software that could, at runtime, allocate our tests to different parts of our test infrastructure, depending on what those things said. So we built one of those. So here's the visualization of that piece of software running. So here is the parallel one. This is the one that this is the bulk of the testing, to be honest. Although it doesn't look like it in this diagram, but we've got one version of the system that's been deployed, and then we have a whole bunch of test runners that are injecting different test cases and running different test cases against that version of the system. Over here, we've got the collection of all of the time travel tests, and each time travel test has its own version of the system, and it's just talking to that. Over here, we've got other forms of sequential tests that are destructive, and so on. And you can this is the visualization that Mark Price wrote when he wrote the distribution code, so that you could visualize what was going on and just understand it a little bit better. But we thought it was pretty, so we kind of kept some of the videos. Finally, we want our tests to be efficient. We want to be able to be there's no real hurdle to us creating as many of these things as we want. And ultimately, we can't have as many as we want. There's going to be economics that stop us, but we'd like to be able to think in those terms. So let's think a little bit about what that means. So first of all, what does it mean in terms of what does production like being? If you're Google, you don't have 2 sets of the Google hardware in order to be able to, one's a test environment and one's the real world. It doesn't work like that. So if your production environment looks like this, and your normal interactions through the system look like this, then this is your minimal test environment. This, you know, you want it to be production-like with respect to deployment and configuration, but it doesn't have to be an absolute clone. So you can have a cut-down version. If some of your interactions are a bit different, you might arrange it differently. But basically, that's it. The other thing about efficiency is to think about, you know, behaviours of more complex systems. Certainly, the sorts of systems that I end up working on, you know, these days systems are big and complicated. They're often distributed, often asynchronous, and that starts to bring in all sorts of layers of complexity. You get race conditions and all those sorts of things. So one of the techniques for thinking about that is that we don't want to surface all of that complexity at the ridiculously high level of abstraction of our domain-specific language. The language of our test cases, we want to be simple and predictable in the way it works. So one of the things is that each instruction in a test case, in our executable specification, will complete before it moves on and executes the next instruction. So it's going to be synchronous at that level, even if the system's not. Our system, when we built the Exchange, was wholly asynchronous. Everything was asynchronous. But the test cases, you would place an order, and when it moved on to the next instruction, that order had been placed or failed, and it would have been you know, the information about it would have been reported back. So we want that to happen. So the nicest way to achieve that end, if we want to hide the asynchrony of a system underneath, is to come up with a concluding event. So if you've placed an order, you have some event that says order placed or order failed, and you listen for those orders, and you don't move on until you see those orders. So that's the best way of doing it. You have the concluding event, and you implement it that way. So here's an example. We've got this is kind of the layer down from our test cases in the implementation of the domain-specific language. And again, this is a made-up version just to try and demonstrate the concepts. So we've got a place order method. That's an instruction. So the test cases would always just talk about placing orders, or whatever. That's the level of abstraction that they would always operate at. We're going to send an asynchronous place order message, and we're going to parse that and get from the parameters that we're given. And we're going to wait for an order confirmation, or we're going to fail with the timeout. We're going to build that in. So think about that as well. What that means is, so we could imagine placing an order and waiting for a timeout. Every single time that we do that, we're going to be using the same bit of code, so that we can make sure that we put a bit of engineering effort into making sure that that code's dead reliable. And he's always going to place the order or timeout in a sensible way. We're not going to be debugging those sorts of things all over the place. We're going to be doing it once and then reusing it across all of our different test cases. And then, you know, there's some stuff that you can, abstraction that you can build into there. If you really, really have to, if you can't find a concluding event, the first thing that I'd recommend is think about your design of your system and think, maybe there should be a concluding event. Maybe I'm missing something in the design of my system, and if I implemented one, it would be a better system. But if you really can't find one, let's say you're writing this test against something that you don't have full control of, a legacy system or something like that, then what I would recommend is in the test infrastructure, you implement a poll and timeout mechanism. So again, shared. So at the point at which it's saying waiting for that, let's go back. At the point it's saying it's waiting for the order confirmation, what that's doing behind the scene is it's going and polling and saying, is it there yet? Is it there yet? Rather than waiting to be pushed the event. So you can do that. What you should never, ever, ever, never, ever, ever do is put waits in, time delays in the test case. I make a reasonable proportion of my living I make going and fixing those kinds of bugs, because those are the way in which you make your tests really flaky, really slow. The best case, let's say you put a wait for 5 seconds to avoid some kind of race condition. The best case is that may work for a bit, and now you're just burning 5 seconds because probably the result happened 5 microseconds ago, and now you're just wasting all of that 5 seconds. And those 5 seconds add up when you start to get to tens or hundreds and thousands of test cases. So the best case is that you make your tests really, really slow. The worst case is, and what mostly happens, is all you're doing is that you're just moving the race condition somewhere else. And it means you're going to end up with more intermittent tests, more flaky tests, and all of that kind of pain. So don't do that. That's really not a good strategy. So I'm on to my 2 summary slides. So don't use UI record and playback systems. Don't record and playback production data. The use of production data has a place, but it's really, really narrow. Be very specific about what it is that you want to test. Be very precise about the state that you want your system to be in for each individual test case, and allow each individual test case to get the system into that state. And use your DSL to make that a fast, efficient process. Don't dump production data into your test systems. It's big, it's heavy, you lug it around. I had a client last year. Their build directory was 114 gigabytes. And when we looked closely, 112.5 gigabytes was test data from production image. So every time they deployed the software anywhere, they were moving an unnecessary 112.5 gigabytes of data, which meant that their deployments were slow. And they didn't, it's just, don't do that. It's just not a good idea. Don't assume that all these wonderful products are just going to solve the problem. There aren't any that I know of that solve this problem. This is different. So there are tools that allow you to work in this way. The Cucumber, SpecFlow, BDD sorts of tools hint at this kind of level of abstraction, but they don't force it on you. And what lots of teams do is that they rewrite the test script, the test infrastructure for every individual test case, in which case you've lost all of the advantages. Think very carefully about this. I'm missing a slide from this deck, which I usually put out, but is this a whiteboard one? Yeah. So if you think about the architecture that we've described, what we're talking about is that we've got the test cases at the top. These are wholly in the language of the problem domain, focused on what we want of the system, not how it works. We've got the domain-specific language that we implement that allows those test cases, that provides the behaviors that these test cases need to fulfill the do. The next layer down, we've kind of talked about implicitly but not explicitly, is we've got these protocol drivers. So when I have my test cases that could work through different channels through the system, through the UI or the fix API, what my system was doing is saying, okay, I've got a protocol driver that understands how to talk to the user interface, through to the web interface, and I've got a protocol driver that understands how to translate place order or anything else for the fix API, and I can they're plug compatible. They've got a business level, place order level semantics at the top, and a prod and poke the system semantics at the bottom. And then at the bottom, you've got the system under test. This is a really powerful abstract model. Gives you the opportunity to go very quickly, write lots of these test cases, have your system change quite radically and dramatically, and not invalidate your test cases at all. And I've not seen any tools anywhere that describe that kind of those levels of abstraction, and I think that they're really important. You can apply these to lots of different tools, but you need to do it yourself. You need to have the strategies in mind yourself. Don't have a separate testing QA team. Quality is down to everybody. Make sure that it's a collaborative exercise. In particular, make sure that the developers are responsible for the acceptance test once they're running. Don't let every test start the application. Separate that out. Have your infrastructure do that. Deploy the application. Make sure it's up and running and ready for use. And only then you start running the test cases. And then you can decide whether you're going to have, you've got more flexibility. You can decide whether each test is running parallel or serially, depending on what you want to do. Don't include systems outside of your control in your acceptance test. Test the things that you're responsible for and focus your testing effort on those. And don't put wait instructions, but if you do, give me a call. I'll come and help you along.
And the previous statement, you want to say that I should not start order several components in my architecture and stub everything to be...
The things that are out, so the step one really is to decide where the boundary of your system is. Decide what it is that your system is, your team is responsible for. One of the things that defines that for me is what's an independently deployable unit in your system. What's something that you can consider being able to develop and deploy without having to talk to anybody else, without having to test any interactions. If you think of that, that's a good way of describing the scope of a deployment pipeline. and the scope of your testing strategy. Okay? So do ensure that developers own the tests. Do focus the tests on what, not how. Think of tests as executable specifications. I think it tends to put your mind in the right place to get some of these things right. Make acceptance testing part of your definition of done. Make it a normal behavior of the team. Initially, when you start doing this with developers who are not used to this level of testing, you're going to get some resistance. You're going to get some little bit pushback. I have yet to see a team that's done this for any moderately reasonable period of time that would ever go back to any other way of working once they've seen it working. Because what this gives you, it gives you such a massive level of confidence to make progress. You can go really fast and you can start focusing on the stuff that we all really enjoy, which is the creative stuff about coming up with cool designs and new ideas instead of the grungy stuff. This allows us to go really, really quickly. Don't get too worried about the idea of building these DSLs. They are much, much, much simpler than you think. The last time I had to, I've had the luxury of needing to implement these multiple times, and so I know the patterns now. They're kind of, I understand them, and that gives me a bit of step up. But the last time I built one of these for a system that I'd never seen before, using technologies that I wasn't really very familiar with, it took me 2 days to build the first 2 test cases that was to establish the patterns in the infrastructure that the team could then take on and grow and build more tests on top of. You do it incrementally. You only have to you focus narrowly first on just the behaviors that you need for some simple test cases, and then as the team, the product owner, whoever needs more features, you implement the DSL that you need to fulfill to describe those, invent the language even, the ubiquitous language, and then implement that as a part of your domain-specific language to allow you to write the test cases, the executable specifications. Do stub external systems to give, remember, I like this this thing of kind of putting probes on my system to measure it. That's what you're trying to achieve. You're trying to get close to your system so you can put it into the state that you want it to be and you can measure it. Test in production-like environments. We want to test not just the code that we write, but the configuration of it, the behaviors of it. So although I said you stub out all of the external bits, the bits that we're responsible for, I'm going to deploy more. I'm going to deploy the language, the operating system, the relational database. I'm going to configure the network for my system. All of those as part of deploying in my acceptance test environment. So that at the point at which I push a button to deploy it into production, I know it's going to work because it's already worked lots of times in the test environments. Do make instructions appear synchronous so that each step in your language, you don't want to be dealing with the horrible complexities of concurrency at the level of abstraction of domain-specific languages. Do test for any change. We tested for everything that we could think of. We tested scalability of our system, the performance of our system, the resilience of our system when bits of it were broken. We tested every user story, every acceptance criteria for every user story. Our default was that we'd write an acceptance test for it. By the time I left, the project's still been going on for many years after I've left, but by the time I left, after about 5 years, we were on every commit, we were running somewhere between 50 and 60,000 test cases, of which about 20,000 were acceptance tests. It's a lot of tests, and we were getting an answer for the whole lot in under 57 minutes. Because you can run them in parallel. You can go wide. And think about the efficiency. So start taking that seriously, because as you start building up these larger and larger test suites, the pain of running them will start to bite. So you need to take that seriously. That's my talk. I'm really happy to take any questions that you've got. I don't know what you want to do in terms of the time for the event. It's entirely up to you. Okay, cool. Cool. Any questions? Thoughts? Do you think I'm insane?
Just clarify something that there is a slide that you show the definition of the test case using FPGA.
Yep.
So that particular kind of dependency you recommend stuff that kind of.
It depends. It depends whether you're writing the FPGA system or not. If that's a third-party thing, then yeah, I'd stub it. If it's something that I'm developing, then no, I'd be testing it this way. I've done. The reason that's there is that I've done that. So I worked in a trading system. We were building FPGA stuff, and there was a lot of the testing that was in simulation because with FPGAs you've actually got to burn the silicon. You've actually got to, and there's physics now, and there's latency, and I wanted results faster than that. So we did a lot of stuff in simulation to get high quality feedback sooner. But at some point you want to run some testing against the real silicon when it's burnt. So yeah. So my philosophy for this whole thing. I have some other talks on different aspects of this stuff, but fundamentally my philosophy is that I think that what we're talking about here is, if we do this right, is a proper engineering approach. And if we're doing this as a proper engineering approach, then what we're looking to do is that we're trying to take guesswork out of the game, really, as far as we're able to. We're never going to be perfect. We can never, ever, ever have enough tests to prove that our software is good, but we can work in a way so that if one test fails, we know that our software is not good enough and we reject it. So what I want to do, if I'm working on some software that's serious, like like an exchange, or I've been working with a client that builds medical devices, people's lives depend on. If it goes wrong, they'll irradiate people and kill them. So there's a kind of high standard with those sorts of systems, and so in those sorts of contexts, I want to test everything that I can think of, everything, and I'm not going to think of everything. Nobody's ever going to think of everything, but I'm going to. The daylight saving things that I talked about, we thought of that one, so we're never going to suffer from a daylight savings problem because we thought of that one. And when something happens in production, we think, we should have thought of that. Let's write a test. That's the first reaction. So I want to test everything. That's kind of my starting philosophy. That's where I go from. And if you want to do that, you've got to do it. You've got to find a way of doing it efficiently, because otherwise that's going to kill you. That philosophy is going to kill you. And this was part of the answer that we came up with that worked for us, because it was so easy to write these test cases. You still had to stop and think about what it was that you wanted, but it's a requirements game now. You think, what behavior would I like of the system? So it kind of starts bringing it together into this quite elegant process of design, sort of at the functional level, and that kind of naturally bleeds into having these executable specifications that we can then use as a tool to drive our development process. Pleasure. Cool. I am talking from a position of deep ignorance. I've seen some conference presentations about it, and I've read a little bit about it, but I've never used it for real on a project. It looks quite nice. I'm a little bit suspicious over the kind of parameterized testing approaches, which I think PACT does as well. But I mean, it certainly does the user contract stuff. And there are some good stories about it doing that in some quite serious environments, with large environments, and sort of defending quite fine-grained microservice architectures and the interface boundaries there. They have some quite good stories about that. So it sounds reasonable to me. The property-based testing, I'm not a big fan, because I like my testing to be dead specific. I want to be absolutely precise about the case that I want to do, and I want to try and think about all of the edge cases. Just throwing a bunch of a range of values at it, I'm not quite so sure about. It feels a little bit back to the kind of, let's just push production data through it and sample, and that's not accurate enough in terms of trying to find the errors. I think there are. Again, in this particular case, I'm talking from a position of ignorance, because I've not really used it on a real system, the parameter-based testing. I've played with it as a strategy on little bits of code, and it didn't help. It didn't help me draw. This sounds very arrogant, but I've come to an approach that works really well for me. And it didn't add anything to my approach. It didn't find bugs that I wasn't finding before. It didn't make me think that it was going to find bugs that I wasn't finding before. So I didn't spend the time, to be honest. There might be something there. There are people that I respect that talk highly of it as a technology, but it's not something that I've seen and that I perceive as such. But that might be my ignorance. Any more questions, thoughts? Yes?
You don't make the case that you shouldn't have separate development and QA teams, but then you approach it from the perspective that that should be maintained by the developers exclusively. So what's the role of the QA team members on all this, or whether there's still a role for or a place for strong teams?
I think that there is, but I think that it's changing. I think I'm a kind of lefty liberal kind of person, and I don't want to do anybody out of a job. But I think that there are certain kinds of jobs that probably their time has gone or should be, and I think the sorts of QA people whose job is to manually interact with the system and read a script and then just be script monkeys. I don't think that's a good use of people. I think it's a bit of an abuse of them as individuals. It's not a very creative thing to end up doing, just be a translator from a script that somebody wrote into a key press thing. I can automate that. So let's automate it, and let's instead get those people doing more creative things. So there are roles for QA people. So I like, my preference when I'm kind of establishing a team is to have some professional QA people as part of the team, because they think about testing differently. They bring a different perspective. They think about stuff, kinds of tests to add that I wouldn't have thought of as a developer. So that's really valuable. They can help out, knock up the first version of the test cases in the domain-specific language. They can help evolve the domain-specific language. Those sorts of things. The other key role that they can do is they can do exploratory testing. So, automated acceptance. So my hardline stance is that I think that there's no role for human beings doing regression testing. We're too slow, too inefficient, and too low quality, and it's an abuse of the human beings. So let's not do that. Let's automate that, and then free people up to do exploratory testing. So there are kinds of things that we're probably never going to write automated tests for. So, does that color of the button, is that better or worse? Or you might be able to do that with A/B testing. I don't know, but is it nice to use? Does it paint pretty pictures inside my head and allow me to think about differently about the system? Does it allow me to explore the system? All of those sorts of things. We might build machine learning algorithms to do that one day, but we're not there yet. So that's a good thing for human beings to do. So I think there are good things, and there's very strong value that professional QA people do. My perception of the people that I've seen go through this journey is that they like it more, and they feel like they're contributing more to the process than just the traditional kind of QA role. So I think it's a positive, but there are some people that might not be up to it. And I think that's a shame, but I think that's just a fact as things move on. Any more?
You talked a bit about performance testing at the beginning, and you placed it after acceptance testing.
Yeah.
We seem to look at the system and the testing as a black box. Do you ever think of performance testing in smaller dosages?
Yeah. The original schematic that I had for the deployment pipeline actually had 2 stages of performance testing in it. So it had component level performance testing and system level performance testing. There's some subtleties in that diagram actually that. So the first thing is that mostly. I've tried gating it in different ways, and it really depends on the maturity of the team. So the first thing is that when in the early days when we were doing this, we would wait to run the performance tests until after the acceptance test had passed, because the performance tests were even more complicated to get right than the acceptance tests, and so we wanted to know that the system was up and running well enough before we wasted times and then had to do horrible things to debug the performance test environment if something went wrong. And the downside with that is that you're just pushing out the time when you get feedback. So nearly always we ended up just running those in parallel. So we'd kick the performance tests off in parallel with the acceptance tests, a different set of hardware. And we'd parallelize each of those. We divided performance for the exchange was critical, and because this was a world-class high-performance system. So from the edge of our network through 2 network hops to the trading system, the exchange itself, and then back out 2 hops to a third party was 40 microseconds. And at that, that point when we did that, that was kind of world class at that point. And so, when you're working at those levels, it's really complicated, the performance testing. And so we took it really seriously. And so kind of in parallel to all of the stuff that I talked about, the test-driven development stuff and the acceptance testing, we had the performance testing in parallel to that. So we did performance test first driven development for some things. So we'd write the performance test first and run it against a blank to prove that the performance test was fast enough to assert at the rates that we needed it to assert at. Because too often we'd write the code, write a test, and say, oh, it's too slow. And then we'd profile it and we'd find out it's the test that was too slow, because it's harder to write the test than the code very often. So we did that kind of stuff. And we did the component level performance testing. We built our own test infrastructure. We had dedicated test runners that would kind of warm up the VM and make sure the optimizer was kicked in before we'd do test runs. We discarded a bunch of test runs and all of that kind of stuff. We did that kind of thing as well. And then after that, we did whole system performance testing, because the component level performance testing was really good at identifying the kinds of errors that we thought that we might likely to have. And then we had the system level performance testing to catch the kind of errors that we never thought of. And so for that, what we did was that this is one of the places where we did use production data. We recorded the worst hours worth of trading that we ever saw in production. We recorded those scenarios, and then we instrumented them in a way so that we could automatically kind of scale them up or down. So we'd have the same distribution of behaviors, kind of approximately the same kind of statistical separation of trading and market making and all that kind of stuff. So it was realistic at some level, but we could kind of turn up the volume. And we used to run every release candidate that went through the pipeline at that hour, but at 5 times volume. So we knew that we could cope with 5 times the worst scenario that we ever saw, the most stressful scenario that we ever saw in production. And then after we'd been in production for about 13 months, we had a worse event that kind of tipped us over the edge and kind of screwed us up anyway. But that's, we took the performance testing really quite seriously. And I've got some of the talks kind of that kind of talk about some of that stuff, but it's a bit, gets into the techie stuff more. Anybody else?
Stuff like feature puzzles and stuff that you apply to the whole delivery cycle.
Yeah.
How does that end up affecting the testing? Whenever there's a talk about duplicating tests?
Yeah. This is a can of worms. Sorry, that's a British phrase. I don't know. We say you open a can of worms if you're kind of opening something that is going to go badly. We were doing continuous integration. Continuous integration is about evaluating all of your stuff together. One of the I mentioned in response, I think it might be one of your questions, but I mentioned earlier that I think that the scope of a deployment pipeline is an independently deployable unit of software, whatever that means. For our exchange, we took the viewpoint that the simplest solution to answering that question of what was our independently deployable unit was everything. So our entire enterprise system we treated as one system. We had in one repository. We tested it all together. We deployed it all together. That gives you some downsides. It means that you've got to have a really good story on the engineering about scaling up your test infrastructure and your technologies to give you feedback that's fast enough. We achieved, and I advise that you should always be looking to try and get a definitive statement. Can I go live with this change in under an hour? Everything, and all of those things, all of those tests that I talked about, every single one of them will report back in under an hour. In our case, it was 50. When I left, it was 57 minutes. to get the performance tests, the stress tests, the resilience tests, the time travel tests, the acceptance tests, the unit tests, every kind of test that you think of. And the downside is that you've got to work really hard to get that feedback. On a system of that complexity and that size, you've got to work hard to get that feedback. The advantage is that you avoid one of the hardest problems in computer science. I think that there are, my own opinion is that there are two genuinely world-class hard things in computer science, kind of almost at the level of quantum physics hard, and they are concurrency and dependency management. That's really, really hard stuff. And as soon as you modularize a system, and deploy those independently, you've got a dependency management problem. So there are ways of dealing with the dependency management problem. This is the microservices route, but to my mind, that's usually a harder problem. And so we took the decision early on for the exchange that we were going to start off treating it as a monolith until we couldn't do that anymore. The architecture of our system was really nice. It was really modular. It would have been really easy to go to a microservices architecture in terms of the software. The dependency management problem it wasn't bad, but it would probably stress us a little bit. We could have done it, but we decided not to. We'd just carry on for as long as that worked, and then we'd tackle it when we were forced to. And we were never forced to, because we could do the engineering to keep up with the feedback, give us the feedback that we needed. I think that there's a little bit of kind of silver bulletism that goes with the idea of microservices. People think it's easier, and actually I think it's harder. That's gone slightly off topic. Sorry, but it seemed relevant when I started, and I've forgotten why. The other part of your question was really about branching is the way that I'm thinking about it. So we're doing the continuous integration thing, and in continuous integration, the best way of doing continuous integration is to evaluate your changes as frequently as you can get away with alongside everybody else's changes. And then you step back from that, and there are strategies for isolating change. One of which is feature toggles. The other one is kind of feature branches. There are other ones, so you can do things like branch by abstraction, you can do dark launching, and there are techniques to allow you to do work on trunk in continuous integration. Feature branching will kind of get you, so far, but it's problematic because any form of branching is about isolating change, and that's true of feature toggles as well. So the question that I think that you were asking, I've got around to it eventually. I apologise. So I think the question that you were asking, I think, is so what's your strategy for testing those things? Because you've got a feature toggle. Are you going to test it with the behaviour turned off, but what you're deploying into production, or with it turned on because that's the new behaviour and you want to get feedback and know what's going on? Or are you going to do both? If you do both, what about if you've got 2 feature toggles? You're going to do all 4? What about if you've got 15? It gets really big problem really fast. The advantage of a feature toggle over a conventional branch is that you're kind of isolating at the level of behavior with the toggle rather than at the level of the code change. And so branches tend to get in the way of techniques like refactoring. So if you've got a broad refactoring across a code base and there's a whole bunch of code hidden away on feature branches, you're either going to screw people up, or you're not going to do the refactoring. There tends to be a pressure against refactoring is usually what ends up, or you just break stuff and it doesn't work very well. So branches are a bit problematic. Feature toggles don't have that problem, but they do have the testability problem. So I kind of have this hierarchy of things. So I start off, and my ideal position is that I want to make a tiny change and push it into production. And it works alongside everything else. That's fine. And therefore, I don't need any feature toggles either. And let me just finish the sequence, and then we'll come back. So that's my first stance. And then if I can't do that, let's say I want to make a bigger change that's a number of steps before it's useful to somebody, I'm going to do dark launching. So I'm going to have a tiny change, release it into production, but people can't use it yet. But I can test it. And then if that's not good enough, then I'll probably do branch by abstraction. I might be doing that anyway because I quite like abstraction and separation of concerns and those sorts of things. It drives my design strategies quite a lot. So I might do branch by abstraction where I'm going to build multiple versions of the code and I can switch them behind. And I might run them in parallel but just throw away the results of the new one. So I can test that live. I can watch what's going on live but ignore the results. Maybe I could do that for some things. And then only if none of those works will I go to feature toggles. And only if the shit really hits the fan and something terrible happens and I really feel like I've failed, will I use a branch in my development approach. Because I think branches are really dangerous. And that's usually one of the more contentious things to say, but let's not go there tonight. If you want to know more about what I said, I've got some stuff on my blog that kind of describes what I think about that and why. Yeah. Yeah.
But there is another scenario that you can create feature branch, and when the feature must be in production, you integrate it with production.
Yeah, and that's what I'm arguing. So I think that's the worst of all worlds. It's not the worst of all worlds, but it's of the ones that we've talked about, it's the worst. So there are other ones that are worse than that. So the problem with feature branching is, I don't want to spend all of the time that I spent earlier in the week because this could be contentious. But the problem is you're deferring feedback. So you're putting off. Any form of branching is about hiding change. Continuous integration is about exposing change. So they're opposite ends of the spectrum. You can't do both. So you can kind of fudge it if you're doing feature branching. So you can do tricks like, you could run all of the tests after you merge it to the head to trunk to master. Okay, you could run all the tests, but then you don't get feedback until you've finished, and that's no good. So you could run it on your feature branch and when you merge to master. Now you're running the test twice, so that's inefficient. So you're slowing the whole the process as a whole is slower. I'm trying to get the process as lean and fast and efficient as I can to maximize the feedback, the quality and speed of feedback. And so I will take the compromise of these other techniques rather than using feature branching. I go into that in much more detail on the blog post, but I just don't want to confuse people by.
The good scenario would be the product owner, so prioritize the stories and before they go to production route. So the best scenario would be these kind of stories is part of this sprint right now. And when we really need of these features in production,
yep, and yeah, that's probably one of the more common patterns that people employ, but it's not continuous integration. I'm a believer in continuous integration. If there's data that says that people that practice what I think of as continuous integration produce higher quality software faster than the teams that do these kind of branch strategies. And that's technically, for me, that's all about this idea of driving for fast and high quality feedback. That's kind of the golden rule. It's kind of what all of this continuous delivery stuff is really fundamentally about. It's trying to work in ways so that I can understand the implications of my change as quickly and as effectively as I can, and as definitively as I can. If I could get my performance test results as a red squiggly line in my IDE, I would take that. I would love that, but I can't, so I don't know how to do that. So the deployment pipeline is second best, and as a result of working that way, it puts compromises on me. It means that I have to think about developing changes much more incrementally, because one of the prime directives of continuous delivery is that you work in a way so your software is always permanently in a releasable state. And so you don't wait until a feature is finished before committing it. You test it and you evaluate it, you get feedback on it, and you're happy for that to go live without it being used yet. That's part of the game. That's one of the compromises that you take in order to get all of these other benefits. And we're way off topic for acceptance testing. Thank you very much indeed for your time. Thank you.